I wrote an essay called Pure UI a bunch of years ago, talking about this idea that was very revolutionary at the time, pretty much inspired by React, of our UI is a simple, pure function of state. So some data goes in, some UI goes out. But in that essay, I kind of painted a picture that was a little bit overly simplistic. Oh, it's just so wonderful. There's just a unidirectional way that data flows in, it turns into UI, and that's the end of the story. But what was missing from that essay is the elaboration of how does data change? So on the heels of a great presentation about change, today I'm going to talk about data changing, data mutating, data living in different levels of state and different levels of consistency throughout the world at any given time, and how we can best reason about it. So I call this talk Consistent UI because a word that probably comes up every single day when you're doing your design work or your product engineering work is consistency. So we think about consistency in terms of UI. We create a design system so that everything looks consistent. For example, I love my border radius all following some rule. But consistency has its roots in logic. And it's basically a quality of no contradiction. What it means, basically, is that a system that is consistent has no two statements that can be proven to be true or false simultaneously. And this is a property that obviously we are very good at detecting normally in our lives. In fact, I'm going to make the case today that without you realizing, you're constantly evaluating the consistency models of the applications that you use every day. You develop intuitions about data being stale when it shouldn't be stale, or a right that you made not being honored in a different part of the UI that you went to. So this idea of consistency is most relevant in the field of distributed systems. And one of the things that I want to incorporate today into this framework for thinking about UI is that when we're creating products, especially modern products that have a lot of client-side state and do a lot of the things on the client, especially when they introduce a divergence of data sets relative to the changes that you're making locally and the changes that you're in the server, we start incorporating the idea of a distributed system. So a term that comes up a lot is this idea of a data consistency model. A data consistency model is simply an idea that if you follow a certain rules of contracts, you're going to get a set of guarantees around order and visibility of events. So everything that happens in a distributed system can be thought of as an event. An event is the idea that something occurred. But when you think about an event happening here, and an event happening somewhere else in the world, an event happening somewhere else in the universe, we need to reason about ideas like ordering. So we start incorporating concepts like partial and total ordering. So if you use Git, you're very familiar with the idea of partial ordering. When you send a PR and you press the squash button, sometimes it gets rejected because the system tries to institute a partial ordering that is consistent between all the participants. Our job as designers and product engineers is to build very coherent, cohesive, and consistent UIs and products. So the traditional definition of a distributed system is quite boring, so I brought today two definitions, the boring and the fun one. So the boring talks about this idea of there is a distributed set of computers all over the world that are networked. So typically, in the types of products that we design today, it means there is a computer that is an iPhone, and there is a computer that is the cloud, or a set of computers usually. And for some of you, you're probably thinking, oh, just the cloud is someone else's computer. That is correct. So we have these different networked computers. And the other part of the definition is that they're passing messages to each other. So typically, you think about some sort of transport like QUIC, HTTP2, gRPC, WebSockets, it doesn't matter. These systems are passing information around all the time. If you're using JavaScript or if you're in the front-end world, you probably think about every time that I need to make a change, I'm going to send a message by using fetch or some API like that. The fun definition is one that you can more accurately relate with things that go wrong every single day, which is you come into the office or you sign on to Slack, and it turns out that something broke because some computer that you didn't even know existed started malfunctioning. So this quote is actually by the creator and father of the concept of a distributed system. And it's the idea that a failure of a computer that you didn't know existed can ruin your local computer. And I think this idea of failure is one that I kind of touched upon on my initial essay that I kind of want to elaborate upon a lot, because the instant that you can categorize a system that you're working on as a distributed system, you are dealing with failure. Now, an issue that I see frequently is that we tend to ignore that the state of failure is even possible. We're very, as designers, we tend to be very optimistic. We go into the design tool and we model a state transition as like, oh, we go from A to B. The network is in between, or I think the network is in between, but everything's going to be good. But in reality, everything is going to be really bad. So one of the main insights that Leslie Lamport sort of brought into this world was he was looking at the paper of special relativity. And he realized that when you're modeling processes that are separated throughout space and time in the universe, you're thinking about a physical system. So when you're reasoning about time, time is relative to each process, just like it is in the universe. So he came up with this insight that the causality of events, sort of the rules that you define for what happened before another event, is actually more important than trying to tame time. So you can, maybe some of you know about an experiment that was run to prove special relativity that involved atomic clocks in airplanes and on Earth. Two airplanes were traveling west and east in the sky, and one atomic clock using cesium, a very precise element, was used to count the ticks that were happening in each place. And when they brought all the clocks together, they found them to be divergent. So at the end of the day, there was no idea of time that was coherent between these three disparate systems. So physical time and timestamps are very unreliable as a way of finding consistency with these disparate systems. So when I talked on Pure UI about kind of the concept of how you can think of your UI as a pure function of data and state, I mentioned that it's becoming more obvious that because design is how it works, I think the job of the designer is not that distant from the job of a programmer. Ultimately, if design is how it works, you're kind of doing a lot of the heavy lifting of a programmer. And the special point that I'm driving today is, I mentioned something at the very last sentence of my essay was, Lorem ipsum has had a good run, let's replace it with data. So I mentioned this not just because Lorem ipsum is a very small set of inputs to test with. If you think about the data that people bring into our apps, just testing with Lorem ipsum is pretty limited. So you end up having situations where like you didn't anticipate that the string could be longer or shorter or in a different language or contain emojis, and it throws off your design. So the main idea that I shared at the end of the essay was, well, it's about creating more realistic representations of what could actually happen in the real world. So when you're a designer, you want to have a really good idea of the state space of the input of your function. And Lorem ipsum is very limited. But I don't think just thinking about the data points is enough. So the point that I'm going to try to make today in this talk is that we also have to reason about how data changes and what are the consistency models to reason about these changes and represent them faithfully in a UI. So using realistic data points is good, but it's not good enough. So at the end of the day, if you're going to embed data into your application, and this application can be modeled as a distributed system, you have to embed this reality of the underlying system in your design. So it turns out that once upon a time, the web applications and websites that we were creating didn't maintain a lot of client state. So for example, you would submit a form on a Web 1.0 website. The message would go to the server, and the server would give you back a consistent read of how it saw the world as a response of your message. So you didn't introduce this idea of a divergence. You didn't have a local little version of the data here and a version of the data there. It was a very simple unidirectional flow. A similar system that you can think of is a terminal or an SSH session, where you're sending signals to a computer, and then the computer is writing back its output, almost like a video stream. So you send an input, and you get back your output. And there is no divergence of state. But the applications that we're building these days are very, very richly stateful. And if they're very richly stateful, and they can be modeled as a distributed system, we have to spend a lot of time thinking about, no pun intended, we have to spend a lot of time thinking about failure and latency. So a very simple case is when you design a input to, for example, change one data point in a remote system. So let's consider a field that is going to change, in this case, the team name. When I submit, as my job as a designer is to think about all the possible error scenarios. But in addition, I want to think about the consistency model that the API on the other side is applying. An example here is, okay, the most naive case is that I hand this mock to my programmer, and I say, just implement this. Well, but the programmer is going to come back to me later, and it can be predicted because it's a distributed system. It's going to be, oh no, like the message can actually fail while it's in flight. So we're not going to be able to save the team. How do we render that on the screen? So because you know that this system is prone to fail in the communication between the local and the remote, you can anticipate that and you can design around it. As consistency comes into the question, another thing that you can start thinking about is, as I press save, what happens if another competing process is trying to save a competing team name at the same time? And how does the server react to that? Now, we go about our lives not thinking too deeply about this because there is some rule of partial ordering that gets applied on the server side that we don't have to think about. So there is some ACID-compliant database, most likely, that is going to arbitrarily decide on an order, and we're going to get back the result. But it's very interesting to see that local consistency also becomes an issue. When I change the name and my name gets accepted by the remote, I expect that as I navigate the website, my name is honored immediately. Because when I reason about consistency, I press save, and my idea of the world, I start keeping track in my head of the consistency model of the application. So to visualize what a correct implementation of these concepts is, I like to use WhatsApp as an example. So my luggage got lost. I'm getting it on Friday, and KLM is responsible. But I love their airplanes. So I went on WhatsApp, and I was like, KLM, I love your airplanes. So this discrete state that someone at WhatsApp delightfully thought about has two check marks. It turns out that every single person, no matter their level of knowledge of distributed systems, over time develops an intuition of what WhatsApp is trying to tell us with those check marks. So when I first send a message, let's go back in time a little bit, the first thing that's going to happen is, because I said earlier, the expectation today of the modern app that you build is that it reacts immediately. So as I mentioned earlier, in a Web 1.0 world, I would have sent my form, it would have gone to WhatsApp server, it would have done some remote data changes, and I would have gotten a consistent read back. But in this world, that's not happening. I'm going to write to a local data store. So WhatsApp delightfully thought about this, and they were like, you know what? We're going to use a little icon to represent the divergence of local and remote state. Because they understood that the instant that they decided to represent it locally, they were splitting the universe into two. So now WhatsApp has, before it had one job, now it has two jobs. Now WhatsApp is essentially tasked with the idea of data replication. Replication is a very common technique in distributed systems. So this idea that you write immediately to the UI is sometimes called optimistic update. But today I'm going to slightly challenge that term. It is optimistic in that I'm seeing it immediately, and I know as a user that it's not its eventual state. And it's designed to give me immediate feedback. But WhatsApp in this case is doing something that I think is far more interesting. So first of all, they're designing a system that can tolerate failure. As soon as they write to the local store, let's bring back the principles of distributed systems, a lot of things can go wrong. Message passing is in an unreliable network, which is every network, is prone to lots of failures, some of which we're not used to thinking about. So the most obvious is the detectable network error, which is I was offline, I open Web Inspector and I see a bunch of error messages. But if we dig deeper into this detectable error error message, we don't actually have any guarantees about what happened to that write. For example, one option is that I did write the message and I didn't get an acknowledgement back. So it's actually possible that there's a split brain where the message is there and my client doesn't know it. Sometimes we implement retrying to tolerate this kind of network condition. So now we have to think about the message potentially arriving more than once. Now you probably can relate in your experience to chat applications that don't get this correctly. And you send a message and you come back later, you make a consistent read from the server, and your idea of the local was there was one message and the idea of the server is completely different. And that's how you start as a user to start judging the consistency of the application. So what I like about WhatsApp is that it's going further and it's teaching me about the underlying reality of the system. The underlying reality of the system is that I don't have the information about whether the message has been sent and acknowledged or not. Then it communicates me when it's been acknowledged. And there's some guarantees associated with that. For example, if I've been using WhatsApp for a while, I can sort of develop the intuition that my device is not responsible for this anymore. And I can destroy my device, and the message will be delivered to the other end. But they go further because they understand that the underlying data model resembles a graph. So they actually tell me if it's been synchronized to the other end, which if you think about the purpose of what we're designing here, that there is a server, that there is a local, that there is GraphQL, is not really that meaningful. What's meaningful is that I'm trying to synchronize some intent that I have in my brain, some event, with someone else's brain, which is typically a person. And then it goes a step further, and it tells me about that other person changing the state of this message. In this case, that they've read the message and they're now ignoring me. So imagine a parallel universe where WhatsApp didn't think about exposing this underlying reality. And you actually don't have to imagine that hard because it happens a lot. So a naive implementation of a chat system that doesn't think about these problems is one where they just don't tell you anything. There is an optimistic write to the UI. And this is a lot of applications, surprisingly, out there. So if we, again, model the problem as a data replication problem, now I'm just lacking a lot of information to successfully navigate the universe. And again, this could be a little bit of an exaggeration, but think about it. Like, there could be emergencies. There could be scenarios where you have very unstable internet connectivity. So you know, even if you're not that tech savvy, you develop an idea of, like, I'm replicating data somewhere. And WhatsApp is giving me an additional tool to reason about this as a user. So users do develop this intuition. So this is one of the main ideas that I wanted to share about today. We've seen this in user sessions where the user acts as an error detector of the system. So sometimes we design systems that update automatically, and the users don't quite develop the trust for them. So they're looking always for specific buttons or a specific UI that is going to guide them throughout the understanding of the data replication logic of the application. And in some cases, they might even develop ad hoc ways. So in this universe where WhatsApp didn't give me that indicator, and I remember I actually would do this in IRC, I would take on the burden of being the validator of the consistency of the message. So in a lot of cases, we tend to also misrepresent this problem space as a cache, and it's most certainly not a cache. This space that we need to think about more is databases. So really what's happening is the instant that I decided that I was going to write that message in the UI prior to it being synchronized to WhatsApp servers, I now created a database that I'm responsible for. It's like when you adopt a puppy and you forgot that you have to, like, clean up after the pee and whatever. So a database has a well-understood read protocol and write protocol. So in this case, a common problem that I see is that people tend to implement optimistic UI by relying on in-memory implementations. But if you think about it from the perspective of a user, you want the strongest possible guarantee of my message being sent to the other end. So if I think about it from a database perspective, if I make this right, typically the way that databases implement this is they will write it to disk. So they will give me stronger guarantees than a cache would, for example, or writing directly to the DOM would, as is the case of an optimistic update, which is, for example, tolerating the failure of the device crashing. So you can think of the read protocol in this case being, I'm going to tell the user that they're going to see that green message on the screen, not just merely optimistically, but after I've committed it to a solid state drive. So again, this is not something that the user will experience every day, but by giving them the highest level possible of guarantee of durability, I've done my job in its completion. I've ensured the maximum level of effort in terms of preserving this message. And again, if we reason about this problem from the perspective of a database, what would happen if I open a new session, a new tab of WhatsApp, and I have multiple instances within one computer? So in the world where I've modeled it as a cache or some in-memory store and not as a database, I'll probably have this idea that I've given up on local consistency. So I wrote a message that is pending on one screen, and I go to another screen, and it's no longer there. So we've kind of failed at preserving this concept of local consistency within the user session. Another common problem here is when you make a mutation to your data and you expect it to see elsewhere in the same application. Or the back button. If I mutate data and I press the back button, local consistency is typically not enforced. So the user gets what's normally called a stale read. Something I think that is an interesting topic of research here is databases typically deal with this idea of snapshotting. So when you press the back button, it's not fully clear what is the right user expectation, right user contract there. Is it that we're going to give them a snapshot and then animate all the changes that we know happened in between? Or is it that we have to honor linearizability of all the reads and writes that I've been making? So the next sort of concern that comes up is like, how do I make this a faithful representation that is coherent across all participants? And I think this is where the idea of delineating the message as being in progress and the message as being committed to a remote data source is very helpful. So to think about this from another point of view, you can think about what would happen if 3 people are asked to write to the same message group. And they're all going to commit their message. But which one is going to arrive first? Now, we could naively implement a time-stamping process, but the reality is that the way that most typically this gets implemented, whoever wrote a message will see it first, and then they're going to see the messages that followed. But it's not really decidable. So is it that the first one should be participant A, participant B, participant C? So this is where, as a designer or product engineer, we need to understand how the backend reasons about this. Because at the end of the day, in a lot of cases, backends need to make arbitrary decisions to establish partial ordering. Sometimes we use logical clocks, just auto-incrementing integers, basically a version. And as in the Git world, everything converges into master. So the job is that when we go from unconfirmed state to confirmed state, we want to give them a coherent view that is shared between all participants. So as we transition, we have an opportunity to replicate data and synchronize with the remote and avoid divergence of scenarios. What we would avoid here is that when we don't want to get into a situation where the user presses refresh and gets an entire divergent different version of the data. So what are the takeaways from applying these ideas of distributed systems to the realm of design? So the instant that you've decided to maintain local state that communicates over the network, you're inheriting and adopting a lot of the problems that are problems of a distributed system. The next obvious insight is that you have to assume failure. Every time a process is communicating to a remote process, failure is a given. You have to assume a continuously diverging data set. All the mutations that the customer is making locally can then face a different reality once they're, or even be rejected altogether. Something to think about is, for example, what happens when you press on a UI a delete button, but your session has expired, or the very entity that you were dealing with was deleted. So we end up with a change of 2 states that are not possible to converge, whereas sometimes they are. For example, I'm attempting to change the team name, but the team got deleted. We have to think about all the concurrent writes in the remote that could impact the next step of my UI. And it's very important that we are in touch with how the backends are actually implemented. As companies scale and as applications evolve, we've found different consistency models that are best adequate for each type of application. So it's very important to understand, okay, are the assumptions that I'm making in the UI realistic with how the actual data storage model works in the remote? And ultimately, what WhatsApp has taught me is that the best products will accurately represent the underlying reality of the system. They don't trick the user. They're not overly optimistic. They tell me where my message is at and whether I've accomplished the goal of broadcasting that information to someone else in the world. Thank you.